Hello friends, I am Diyanka Chakraborty. In my previous video, I was discussing about the intrinsic semiconductor. Today, I will discuss about the extrinsic semiconductor. So firstly, if you want to get my upcoming videos, then first subscribe my channel and you will get all the videos. So we know the role of electronics in our daily life. Okay. So what is extrinsic semiconductor? We know about the intrinsic semiconductor or pure semiconductor, where there is no impurities. That is called a intrinsic or pure semiconductor. But when we add some impurities in a pure semiconductor, that is called extrinsic semiconductor. The addition of a small percentage of impurity atoms to a semiconductor is called doping, and the impurity that is added is termed dopant. So, a semiconductor having the impurities is known as doped, impure, or extrinsic semiconductor. So, depending upon the impurities, an extrinsic semiconductor can be of two types. One is N-type semiconductor and another is P-type semiconductor. So now here we see the periodic table. This is a group 4 column. This carbon, silicon, germanium, these are the group 4 elements which has 4 valence electron in the valence shell. In group 3 column, there are boron, aluminium, gallium like this. These are the group 3 element or trivalent element. These have the 3 valence electron in the valence shell. And these nitrogen, phosphorus, arsenic, antimony, these are the group 5 element or pentavalent element. This has 5 electrons in the valence shell. So the electrical conductivity of an extrinsic semiconductor is controlled by the excess free electrons or holes produced by the impurity atoms. In germanium or silicon, addition of group 5 element like phosphorus, antimony and arsenic produces excess free electrons, whereas group 3 impurity elements like indium, boron, aluminium creates excess holes. So, what is N-type semiconductor? When we add a pentavalent impurity in a pure semiconductor, that is called N-type semiconductor. Let a small amount of a group 5 element such as phosphorus added to a silicon crystal. So, the phosphorus have 5 valence electrons in its valence shell. 4 of the 5 valence electrons of the pentavalent impurity atom will form covalent bonds with the 4 valence electrons of the neighboring silicon atoms. The 5th valence electron of the impurity atom is loosely bound to it. Therefore, this electron can be easily detached from the atom and set free. So, like this. So, we know the small amount of pentavalent impurities is added to a pure semiconductor, then it is known as N-type semiconductor. In an N-type semiconductor, the electrons are the majority carriers and holes are the minority carriers. Okay. So, this is the energy band diagram of N-type semiconductor. The addition of pentavalent impurity has produced a number of conduction band electrons, that is free electrons. The 4 valence electrons of pentavalent atom form covalent bonds with 4 neighboring silicon atoms. The 5th leftover valence electron of the pentavalent atom cannot be accommodated in the valence band and travels to the conduction band. So, when donor impurities are added to a semiconductor, an allowable energy level corresponding to the loosely bound valence electron is introduced in the forbidden gap just below the conduction band. Since the impurity atoms are located far apart in the crystal, their interaction is negligible. Therefore, the new allowable energy level is a discrete level that is called donor level. Here we see that the donor energy level. For germanium, the donor level is about 0.01 electron volt, and for silicon, it is about 0.05 electron volt below the conduction band edge. However, the exact position of the donor level depends on the impurity type. So now, the N-type conductivity. When a potential difference is applied across the N-type semiconductor, the free electrons donated by the impurity in the crystal will be directed towards the positive terminal, constituting the electric current. As the current flow through the crystal is by free electrons, which are carriers of negative charge, therefore, this type of conductivity is called negative or N-type conductivity. So now, what is P-type semiconductor? When we add trivalent impurity with a pure semiconductor, that is called P-type semiconductor. Let small amount of group 3 element like aluminium be added to a intrinsic silicon semiconductor. If a trivalent impurity atom replaces the silicon atom, only 3 of the 4 covalent bonds can be filled. As the impurity atoms accepts an electron, it becomes a negatively charged immobile ion. Since the impurity atoms accept electrons, they are called acceptor or P-type impurities. These impurities produce excess holes which carry positive charges. Therefore, the semiconductors containing accepted type of impurities are known as P-type semiconductor. So we can say that in P-type semiconductor, the holes are the majority carriers and the electrons are the minority carriers. So this is the energy band diagram of P-type semiconductor. The addition of trivalent impurity has produced a large number of holes. However, there are a very few conduction band electrons due to thermal energy at room temperature. But the number of holes far exceeds the number of conduction band electrons. The unfilled energy level produced by the introduction of P-type impurities in a semiconductor lies just above the valence band. This allowable energy level is called the acceptor level. Here we can see the acceptor energy level. Though the exact position of the acceptor level depends on the type of impurity, it is about 0.01 electron volt for germanium and about 0.05 electron volt for silicon above the valence band edge. Since a very small energy is needed by an electron to leave the valence band and occupy the acceptor level, the acceptors are fully ionized at room temperature. So, this is the P-type conductivity. When a potential difference is applied to the P-type semiconductor, the holes donated by the impurity are shifted from one covalent bond to another. As the holes are positively charged, therefore, they are directed towards the negative terminal, constituting the hole current. So, this is the overview of extrinsic semiconductor. Here we can see the donor impurity contributes the free electrons and acceptor impurities creates the hole. So that's all for today. In my next video, I will discuss about the diode and the diode circuits. So if you like my video, then please like and subscribe my channel, and you can also give me some suggestion to improve my videos. And if you want to get any idea about any other topics of electronics, please drop it into the comment box. So thank you and goodbye. Stay safe.